we're going to work with two special types of series, Taylor and Maclaurin series. The definition of Taylor series is equation number 6. It is our power series with a little twist to it. We have some factorials in there. All right, our notation is f, which looks like it's raised to the n power. Well, when it's f with a 0 up here, that's your normal beginning function. When we put a 1 in there, that's for the first derivative. When you put a 2 in for n up there, that's the second derivative, then the third derivative, and so on and so forth. So we have this new n factorial in our denominator. Now, this Taylor series, again, is centered at a. All right? Now, we have a special case if a is 0 on our Taylor series. Then we have equation 7, which is known as the Maclaurin series. All right, so what we want to be able to do is to change our functions to one of these two types of series. All right, so let's find the Maclaurin series for f of x equals e to the x, and let's find its radius of convergence. So here's the Maclaurin series. So what we want to do is we want to first start listing out a couple terms so we can start writing out the series and find the pattern to how we're going to write our summation for our series. So when n starts at 0, that's f with the 0 up here. That's your normal function. F of x is e to the x. Then we're going to plug in 0 into our function, and e to the 0 is 1. All right, let's try this for n is 1. And we usually want to do about maybe n equals 3, 4, 5, somewhere up in that area so we can see the pattern. So the first derivative of f of x is e to the x. Well, this will be nice because that won't change. The first derivative of 0, so f prime of 0 is e to the 0, which is 1. And it looks like that's going to stay the same all the way through. So I found my pattern. So we're going to write this out in this format right here. We're going to list out some of these terms to find the pattern. So the summation will become x to the n over n factorial. Well, f to the n of 0, whether it's f prime, f double prime, or f triple prime, it's always going to end up as a 1. So this cancels out our numerator to a 1. So we keep our 1 over n factorial times x to the n. So here is our summation for, or a Maclaurin series for f of x equals e to the x. So if we write this out, give us a couple terms. We have the 1, then x to the first. Remember here it was x to the 0 over 0 factorial. So we're just left with 1. X to the first over 1 factorial plus x squared over 2 factorial plus x to the 3 over 3 factorial, so on and so forth. So if we want to find r, we have to do the ratio test of our Maclaurin series here. So the limit of, this will be the n plus 1 sequence, so x to the n plus 1 over n plus 1 factorial, divided by our original sequence fraction here. But, we multiply by the reciprocal instead, so times n factorial over x to the n. And we can do some canceling here. X to the n will cancel out all of these except for 1x. N factorial will cancel everything out except for n plus 1. So the limit as n approaches infinity is going to make our denominator bigger. Our x is going to be locked in at some value. So this is going to become 0 for our limit, which is less than 1. So this converges, come back here, this converges for all x, so our radius of convergence is infinity. All right, so let's consider, just so you can see a graphical approach of what we're doing, similar to what I showed you in the last video. Here's our Taylor series function, t sub n of x. And this is the definition for our summation for the Taylor series. Unbelievable, this mouse. All right, so if we start to look at our function y equals e to the x in red, and we start listing out our partial sums, if you will, here is t sub 1, which is this line, which kind of overlaps it for a small brief period. But the more partial sums we have, now the closer our curve is coming to the red line at some point in time. So here's t sub 3, which is getting closer and closer for this period of time. And if we keep doing this all the way out to infinity, then it's going to pretty much map out that curve. All right, so these Taylor polynomials, and they're also our partial sums. All right, let's find the Maclaurin series of f of x equals cosine of x. So again, we're going to make a table. I had to spread this out a little bit because I got to fit cosine in here. So we start with 0. So f of x equals cosine of x. Cosine of 0 is 1. Next, let's test the 1. The derivative of cosine is negative sine of x. So then we're going to find f prime of 0. And sine of 0 is 0. Then we're going to try n is 2, so the second derivative. So the derivative of negative sine x is negative cosine x. And then we evaluate the second derivative at 0. So 0 cosine of 0 we said was 1, but now we make it a negative 1. Then when n is 3, our third derivative, the derivative of negative cosine of x is back to sine of x. Then we plug in a 0, that's still a 0. When we get to 4, now we're right back to where we started up here. We're back to the derivative of sine of x is cosine x, and we're back to a positive 1 for the fourth derivative of 0. So plugging in our Maclaurin series summation rule, and we start to list out some terms here. F of 0, f prime of 0 times x to the first over 1 factorial. So what's going to happen is, remember, we had some zeros here. So let's keep track of those zeros. This one was a 0. This one was a 0. So it looks like to me that every time we have an odd value for n, we're going to get a 0 in the numerator. Now, we had alternating signs on our 1. Our first f of 0 was 1. Then when n was 2, was a negative 1. Then when n is 4, it's a positive 1. And that's going to continue on in that pattern. So this is what I see as my series if I were to write this out with some more terms. 1, then plus the 0, minus x squared over 2 factorial plus the 0, plus x to the fourth over 4 factorial plus the 0, minus x to the 6th over 6 factorial plus 0, plus x to the 8th over 8 factorial, and so on and so forth. And there's those alternating signs taking place. So we get rid of the zeros. We write this out now with no zeros in there, and we look for a pattern. So I can see that I need to have x raised to some power that's going to always give me double my n value. So when n is 0, 2 times 0 is still 0. That's still going to work. When n is 1, then 1 times 2 is x squared. When n is 2, 2 times 2 is 4. When it's 3, 3 times 2 is 6. So we need x to the 2n power. We started out with a positive here, so negative 1 to the 0 power starts out as positive, and then it alternates. And then on the bottom, we need to double our factorial again, just like our powers up in the numerator. So we're going to have 2n factorial in the denominator. So now that we've established the Maclaurin series, let's take its ratio test to find out our radius of convergence. So by doing the ratio test, let's take all of your n's and put an n plus 1 in. So again, remember that 2n on the inside of the parentheses for the power and the factorial will become 2n plus 2. 2n plus 2 when you distribute into 2. Then we're going to, of course, divide or multiply by the reciprocal of our fraction down here in our Maclaurin series. And now we're going to do some cancellations. So again, this is 2n plus 2. So we're going to have some extra x's left over, just like in our factorial. 2n plus 2 factorial. We're going to have a 2n plus 2 and a 2n plus 1. And then we finally get to the 2n factorial that we can cancel. So that's what happened with my factorials. Up here, x to the 2n plus 2, x to the 2n cancels out everything except for the plus 2, so that's the x squared. And with your negative ones, we cancel everything out except for 1 negative 1, which we don't have to worry about anyhow because we're going to take the absolute value of that. So as n approaches infinity, of course, our denominator is getting bigger. So we're going to approach 0, which is less than 1, which tells us our r is going to be infinity. It converges for all of our x's. All right, let's find the Maclaurin series for f of x equals x cubed times cosine x. We just did cosine x right back here. So when something like this happens, steal this answer. Don't do the work again. Steal this. We know that f of x, which if it's cosine x, equals this Maclaurin series. Okay, multiply x to the third to cosine x, then multiply x to the third to the Maclaurin series that we established. Easy money. Well, if we multiply x to the third up to this x to the 2n, we're going to have to add a 3 to it because we're going to add our exponents. And there's our Maclaurin series. All right, example 4. Find the Taylor series of f of x equals the natural log of x at a equals 2. Okay, Taylor series, we're centered at 2, so I'm going to go back and rewrite equation 6 down so I follow everything here. Again, I'm going to start filling out my table so I can start building my series. So when n is 0, we're going to have f of x, which is our natural log of x, and then we're going to take the natural log, or f of 2. We're going to put that 2 in because that's your a value. Before, a was 0 for the Maclaurin series. Now we actually put that value of 2 in here, so that's the natural log of 2. We put in a 1, so now we have to take the derivative of the natural log of x, that's 1 over x. So we put the 2 into this function, that's 1/2. When n is 2, now we take the derivative of 1 over x. Remember, that's like saying x to the negative 1. So we're going to get that negative 1 when we bring it down to the front to multiply to the x and subtract 1 from the negative 1 to make it a negative 2, which now makes it over x squared when we went positive exponents. Plug in the 2, so that's going to be negative 1 over 2 squared. Now I'm not going to write down 4. I want to see the pattern in the denominator with these 2's. When 3, now think of this as that negative 2 up on top. Negative 2 multiplied to the negative 1 becomes positive 2. Subtract from the negative 2 makes it negative 3, so move it to the denominator. Even though you have a 2 on the top, don't cancel this here. So we want to put the 2 in for the x, and so we want to leave this as 2 over 2 to the third. To the 4th power, okay, I'm starting to see the pattern. That negative 3 gets multiplied to the 2, makes it negative 6. And I subtract 1 from the negative 3, makes it negative 4, which becomes x to the positive 4 in the denominator. So that's negative 6 over 2 to the 4th power. All right, so when n is 5, Now we're going to take the 4, the negative 4 if you will, multiply it to the negative 6. That's going to change it to a positive 24. I'm seeing the pattern. We're going to have alternating signs here all the time because of that multiplying of that negative exponent. So we put our 2 in for x here at x to the 5th, so that's 24 over 2 to the 5th. So I think we got enough terms, so let's write out. Now I broke this down a little bit into pieces. I broke this apart. So here's my f of a for when we're doing the function in the first derivative, second derivative, and so on, times, I wanted to separate this as 1 over n factorial, times the binomial x minus a, which in this case x minus 2 to the n power. So this is what our Taylor series is going to start to look like. So now we just have to put in the numbers here that we created right here in the last column of this table. So we first start out with the natural log of 2. Then we're going to have plus, because we're still positive, 1/2 times 1 over 1 factorial times x minus 2 to the first power. So if you want to put a 1 at the power, you still can. Then it's minus, because of that negative, 1 over 2 squared times 1 over 2 factorial times x minus 2 squared. Then we're going to plus 2 over 2 to the third times 1 over 3 factorial times the x minus 2 to the third. And then minus 6 over 2 to the fourth times 1 over 4 factorial times x minus 2 to the fourth. And since we did the 5, let's put that one in there as well. So plus 24 over 2 to the 5th times 1 over 5 factorial x minus 2 to the 5th power plus, and then this pattern just continues going onward. All right, so here our very first term is a constant value. It's not part of this pattern that I notice over here. When n equals 1, here's this term. N equals 2, n equals 3, 4, 5. So we need to start building a pattern. So your 1, your 2 is the power, 3 is the power, the factorials, and we just have to, wait a minute, 2 to the first, 2 to the second, 2 to the, so we're going to write a summation of just these terms right here. So that's going to be the natural log of 2 plus the summation. Now we have that alternating sign we got to worry about. We want the first sign to be positive, so that's negative 1 to the n minus 1 power. So when we plug in the 1, minus 1, that's 0, so that turns it into a positive. That's what we want. Then they're going to alternate. Then we're going to have the 2 and the 2 and then our n factorial, if you will, on the bottom. So 2 to the first, 1 factorial, 2 squared, 2 factorial. So there's your denominator right there. And then our binomial on the top is x minus 2 to the n power. Now again, I didn't put it up in the numerator, all right, because I have these numbers above the 2 to the power that I have to put up there, and we notice that there's a pattern here. That 1 is 0 factorial, this 1 is 1 factorial, this 2 is 2 factorial, 6 is 3 factorial, 24 is 4 factorial. So we should have noticed that when we were multiplying to get those numerators, that's the beginning of 1 times 2 times then a 3 times a 4 times a 5. So we want to put n minus 1. So when n starts out as 1, we want a 0. When n is 2, we want 1 factorial. When n is 3, we want 2 factorial. So we want to be able to rewrite all of this with n's. And now we've created our Taylor series. There it is. All cleaned up. Okay, what we can do a little simplifying here. N minus 1 factorial, here's n, then times n minus 1 factorial, so that's what happened to the n minus 1 factorial on the top. It canceled within this n factorial, so it leaves us just an n. And there's our Taylor series. All right, so taking this Taylor series and now finding r, we have to do the ratio test. So every place you see the n, you have to add a 1 to it. So n minus 1 plus 1 is n. Then the x minus 2 to the n becomes n plus 1. 2 to the n plus 1 times n plus 1. Then we take this and multiply it by its reciprocal, so 2 to the n times n over negative 1 to the n minus 1, and our x minus 2 to the n power. All right, let's start cleaning this up. 2 to the n and 2 to the n plus 1 leaves me a 2 on the bottom. The n over n plus 1 won't change, so I want to group those together. X minus 2 to the n power and x minus 2 plus 1 will cancel everything out except for the plus 1, so I'll have one binomial up here. And the same thing as I'll have a negative 1 up there. So there's my negative 1 times x minus 2 over 2, then times the n and the n plus 1. And remember, we talked about grouping those together because that's the part we're going to take the limit of. And again, remember, negative 1 in the absolute value bars is just going to basically disappear. So here's keeping the n and the n plus 1 together. Here's my variable expression and any scalar values staying together, and leave them in your absolute value bars. This limit is going to approach 1, so our answer is the absolute value of x minus 2 over 2, and this converges when it's less than 1. So to find our radius, we have to isolate the x minus 2 from our series up here. So we multiply the 2 over to the 1. It's positive, so we can take it out of the absolute value bars. And so 2 is going to be your radius. All right, it's important to know this Maclaurin series, and I'm going to pick up with this in the second video. So much open here. Come on.